All right, measurements. One of the hardest things to teach students, that's for sure. But your data is only as good as your measurements. And if you take crappy measurements, you're going to get crappy data. Okay, so measurements always have two parts, a number and a unit. If I say that my son is 5 years old, 5 feet tall, 5 pounds, 5 kilograms, like what do I mean by 5? 5 needs a unit. You need something there to tell me what the number means. And so if you give an answer that doesn't have a unit on the end of it, it's wrong. And it's got to have a unit as part of it. That's always essential. Okay, so they must have both. Like I said, it makes no sense to say that a book is 5, and if you don't have the unit, it is wrong. Okay, so let's talk about grouping of measurements. We can describe them as accurate, precise, both, or neither. Measurements are considered accurate if they are close to the accepted or actual value. Okay, so like close to the bullseye. Precise means that they're close to each other. That means you're doing good, consistent measurements. They were just off. Okay. When we're doing science, we want to be precise. We want our measurements to be close to each other because it says that we're at least reading it consistently. Because to me, precision is a measure of consistency and how carefully are you trying to do it. Okay, and then something can be both or it can be neither. Okay, so we can just look at it that way. When we're talking about this type of data, we also generally tend to look at error. And we generally tend to work in what we call percent error. And if you look at the percent error, you may not remember this from math, but these bars are called absolute value bars. And what they mean is it's always going to return positive. Because with percent error, we don't care if you're over or under, we just care that you missed. And it's just a measure of how far you missed. And it doesn't matter whether it's above or below. So the percent error is always going to be positive. So like I said, so it's always going to be positive on top. And if you don't know the exact value or the accepted value, you can use the mean of your measurements. There's a lot of, I'm not a statistics major. There's a lot of statistics that goes into doing that. All right, let's talk about actually making measurements in chemistry. So hopefully, once again, from your teaching and your other experience, you have some idea of how to do these, but just I still want to cover them anyway. All right, length. Start with one end at the 0 mark. You may be laughing at that I even had to say that, but I had students who had a first grade teacher who taught them that they needed to put the end at 1. How that person thought that, I don't know. But you got to put it to 0. Okay. Then we're going to, so depending upon the last size of the tick mark, you'll need to estimate the last decimal place. Okay. So, for example, looking at this marker, it ends just before the 8 centimeter mark. Okay. And that level of precision that you need is going to kind of vary depending upon what's being measured. So, here I am, I'm measuring something relatively small. If I just said, it'd be really hard to see what that is in between. You could say that it's 7, like if you had a magnifying glass, you could say, hey, that is 7.96 centimeters. Something like that. But millimeters are really small. And so usually I would probably say that that's 8.0. I'd probably go to the closest millimeter just because that's what I'm capable of reading without a magnifying glass. But the bigger you are, the less accurate and precision you need, the less you need there. So you don't have to estimate that last place so much. All right. Volume, liquid volume specifically. We're going to use graduated cylinders, which is what this is, or a volumetric flask. If you're not familiar with a volumetric flask, you can probably find a YouTube video on how to do them. They're not very common unless you are making solutions for a lab. And I'm usually not making solutions that need to be that horribly accurate that I need to pull out a volumetric flask, at least for a high school chem lab. But I do have some in my lab. So if you need any questions on how to use one of those, I can help you with that. All right. So the water level will usually have what we call a meniscus or a curve at the top of it. So right here, it's going to adhere to the sides a little bit better, and so it generally tends to be a little bit higher on the sides, and then it dips down and kind of goes like this. Okay, it's critical that you're always measuring that at eye level, and that you're reading the bottom of the meniscus. So you're always going to make sure you have it on eye level. This guy's not making me too happy because he's holding it. You would want the graduated cylinder on the table to keep it stable. You can have your hand on it, but don't just hold it in the air like this. But you want to have your eye level even with where you're measuring, because if you're high, you're looking down, that's not an accurate measurement. So it's got to be eye level, and you got to read the bottom of that meniscus, right? And then different graduated cylinders have different tick marks. It could be a milliliter, it could be a tenth of a milliliter. I've seen some that are like 0.4 milliliters, which is just really hard to estimate values when you're looking at that as a weird tick mark. But look at your tick marks, figure out what each tick mark is, and then use that to estimate where you need to be. You can usually estimate one more decimal place past that. All right, mass. Hopefully, you get to use digital scales. Key thing on a digital scale is to try to limit the effect of air movement and how that can affect your final results. But don't have students walking around. You can put file folders around them, that kind of thing, to keep it from getting too windy and blowing the measurements around. So depending on the precision of your digital scale, you may have to estimate the last decimal place. So if you have a decimal scale that's going to thousandths of a gram, that thousandths place is going to jump up and down. It's not going to stop and be still. And so you're going to have to estimate what you think that last place is. If you have a triple beam balance, then estimate one decimal place beyond that last tick mark. If you have those, I can kind of guide you through how to read them. They are a little more annoying and difficult to use, but they are usable. Digital scales are great, and they're not too expensive anymore. So I would encourage you put those in your budget if you can, if you don't already have them. All right, so that's making measurements. All right, so now we need to look at units of measurements. So we have the SI unit, which stands for International System. You may be wondering why it's not IS system. That's because in French it is the Système d'International, and all the big key things that they use to measure these things are in Paris. So it's French. Okay. Everybody uses SI system except for America, Liberia, and Burma. It is an easy system to use, but yeah. So, all right. So length is meter, mass is kilogram, time is second. Notice mass is kilogram, not gram. The metric unit is gram, but the SI unit is kilogram, because a gram's just too small. A kilogram is a little bit easier to use in terms of stuff. Area, volume, we use liters, pascals for pressure. Temperature is Kelvin. If you're not familiar with Kelvin, Kelvin is just taking Celsius and adding 273.15. The reason being, that's what we call, it basically makes it, Kelvin has no negatives in it. Because the coldest possible temperature is negative 273.15 Kelvin, Celsius, which we call 0 Kelvin, or absolute zero. And so the Kelvin scale has no negatives, which we have to have in order for doing gases. But in terms of like everyday usage, Celsius is fine, but technically the SI unit is Kelvin. And then energy is joules, and moles is for amount. Okay, key thing to the SI unit is that it uses prefixes. And so these prefixes always mean the exact same thing, always. So the way I like to think about it is 1 kilogram is 1,000 grams, or 10 to the third grams. 1 kilometer is 1,000 meters. 1 kilosecond would be 1,000 seconds. Okay. Same thing with giga. It's a million billion. Okay. So 1 gigameter is 1 billion meters. 1 gigagram is 1 billion grams. 1 gigamole would be 1 billion moles. Whatever the unit is, that goes in there for X. Okay, and so we can change those around. You do need to memorize these. I've had various people try to come up with some way of memorizing these in order. But notice they go by threes, with one exception, centi. And so centi is 2. Then it goes by threes again. You will see some books that include like deca and deci here. I've never used them in my science career. I think a deciliter is related to something in terms of cubic, whatever. But like you don't use it. And so I don't teach those. So just stick to the main ones here. From tera down to pico. I've seen some books go down to femto, which is the one after pico, 10 to the negative 15. But, it's not needed to go that far. All right. Symbols, capital letters for the first 3. Everybody else is lowercase except for micro. That is the Greek letter mu, or the lowercase Greek letter mu. And so that is used there for that. So in the workbook, you'll kind of see these, kind of practice filling them out, try to get used to it, and try to memorize it. Because we're going to need to know these when we get to conversions in the next lesson.